Howdy. As promised, I'd like to take a few minutes, to develop a couple of shortcuts, a couple of formulas that come about by substituting into the equations of motion. You recall that so far our two equations of motion have been v equals v0 plus at, and delta x is equal to v0t plus 1/2 at squared. And both of these are valid when the acceleration is constant, meaning not changing over time. And what we learned today in class is that we can sometimes solve problems when we are missing two variables by using these two equations in order to solve for the two variables that we are missing. But we also discovered that that was an algebraically intense process, and so we wondered whether it might not be simpler to go ahead and pre-solve for variables and come up with formulas that would be useful when some information is not given. In other words, maybe I could take these two equations right here and I could maybe solve for A and eliminate A out of the equations so that if I'm not given acceleration, then I don't have to worry about it. Let's actually try that. What I'd like to do is to take these two equations and combine them with substitution by substituting A away. And it's going to look like this. I'm going to solve for A in the top equation by subtracting v0 from both sides, and I'm going to divide both sides by t, so that I get A is equal to v minus v0 over t. Incidentally, if you take a close look, you can see that this is actually the change in velocity over t minus 0, which is the change in time. So really, we've just rediscovered the definition of acceleration to begin with. But anyway, carrying on. Now that I've solved for A in the top equation, I can take that and substitute it for A in the second equation. And that gives me delta x is equal to v0t plus 1/2 of what A is times t squared. Often when you substitute, things look really yucky, and then they start simplifying. And that's certainly the case here. Because one factor of t cancels, and now I can distribute, let me distribute my t like so, so that I get 1/2 of vt minus 1/2 of vot. Looks like I distributed both of them. Couldn't help myself. And furthermore, I notice that I have two terms that are like terms, vot and negative 1/2 vot. So then when I combine the like terms, I get 1/2 vt plus 1/2 of vot. Take a look at that carefully. This is 1 vot minus 1/2 vot is 1/2 vot. Now this is a perfectly good formula that gives us delta x without acceleration. But I actually gain some additional insight if I factor out the t and the 1/2 to get 1/2 of v plus vo times t. And we notice that this expression right here, 1/2 of v plus vo, is actually the arithmetic mean, or the average, the mean of the initial and the final velocities. That means like plus there. It's the mean of the initial and final velocities. So this is actually saying something profound. This is saying that my displacement is equal to the average velocity times the time. Ah, that's very, very interesting. Well, having generated a third equation of motion to go along with my other two, I wonder if I could have done the same thing But instead, at this point, instead of solving for A, what if I had solved for T and substituted to get a formula that's useful when I don't know T? And it turns out I can do that also. I'd come back to here and solve for T, then I would divide both sides by A, and find out that T is equal to V minus V0 over A. And it turns out that if you substitute into here, you get a nice relationship. Since T is equal to V minus V0 over A, I can replace T with what it is. And now as I consider the multiplication, I see that I have a factor of 2 and a factor of A in the denominator. So my denominator will be 2A. And at the top I have this very interesting expression, V plus VO times V minus VO. And if you remember your Algebra 2 at all, you remember that that is going to give me V squared minus VO squared. And all of that is still equal to delta x. And this is also a perfectly good equation that gives us delta x when we don't have time. Usually, we multiply both sides by 2a and add v squared to both sides so that we get our fourth and final equation of motion, what I call the timeless equation because it has no time involved with it. V squared is equal to VO squared plus 2a delta x. Now at this point, you may be thinking, do I want to memorize these equations or do I want to bother and just use the algebra to solve? And to a certain extent, that's a matter of problem-solving taste. What will eventually happen is that if you get tired of doing the algebra, you'll say to yourself, hey, I need to remember these two other equations because situations like them show up so often. And that's actually what I would recommend in this particular case. Let's consider the downsides and the upsides. If I only memorize my first two equations of motion and rely on algebra, then the upside is less memory required. That's always a good thing. On the other hand, it's more work to use my two equations to get where I want to go. If, on the other hand, I try to memorize, then I have to take up more memory to do that. I have to work harder to remember the four equations and not get them confused and so on and so forth. On the other hand, when I need to solve a problem, I don't have to work as hard to do it. Hold on to this thought right here, and we'll come back to it. But I want to show you, demonstrate to you that this really does, these two new formulas really do involve less work. Let's go back to number 23, which we solved in class. And in number 23, we have the problem, a light plane must reach a speed of 33 meters per second in order to take off from the runway. How long a runway is needed if the constant acceleration is 3.0 meters per second squared. Now in class we solved this problem with two equations and two variables. But I want to show you that our new equations can solve the whole thing really quickly. If I take a look at what is given to me, what is given to me is a final velocity of v. 33, not 30. An initial velocity is implied. v0 is equal to 0. The plane is starting from rest. The acceleration is given as 3 meters per second squared. And what we are looking for is the delta x, the length of runway. And if you go back and look at the equations that we just generated, equation number 4 is perfect for this situation because I have b, I have b0, I have a, and I'm looking for delta x. So instead of two equations and two variables, boom, I can say v squared equals vo squared plus 2a delta x, and therefore 33 squared equals 0 squared plus 2 times 3 times delta x. And a quick calculation should give us, let me do that quick calculation here. (33 times 33 divided by 2 divided by 3 is 181.5 meters, or 180 meters when you round to 2 sig figs. That's fairly impressive. This was a lot less work than two equations and two variables. And so that suggests that maybe I want to remember all 4 equations. I think I do. But the problem is my memory does play tricks on me. So the question is, what's the best way to remember these equations of motion? The best way to remember delta x equals v plus vo over 2 times t, which was our third equation that we just generated. And our fourth equation, v squared equals vo squared plus 2a delta x. The best way to remember those is to derive them using algebra a couple of times for yourself. And that way, if you forget them, you can figure them out again. And if you don't forget them, then great. Derive them using algebra. And I'll just go back how that and review how that derivation goes. We start with our two equations, v equals vo plus at, and delta x equals vot plus 1 half at squared. And if I solve these two equations for a and substitute into the other one, then poof, out comes delta x equals v plus vo over 2 times t. You try it. Pause the video, do exactly this, solve for a and substitute, and see that your delta x comes out. If it doesn't work out for you, go back to that point in the video where we derived it, look at it again. Practice doing it. Once you've done it 2, maybe 3 times, I promise you, you will not forget it. Well, once you have the delta x equals v plus vo over 2t, then you can go back and solve here for t instead, and substitute into here, and out will come the fourth equation, v squared equals vo squared plus 2a delta x. And again, I invite you to pause the video and actually do that derivation for yourself. And once you've done it 2 or 3 times, you will not forget that formula. This is the way that the smart mathematicians and physicists remember their formulas. They do it by deriving them, so that the logic of those formulas makes sense to them.